Okay, welcome to Stat 310 Lecture 5. Now we're kind of moving on to setting some of the key frameworks that we'll be looking at throughout the course. And so in particular, we're going to finish our discussion on Chapter 6, where we looked at, in particular, the independent normal sample and distributions related to that. And then we're going to move on to Chapter 7, which really starts to get into the idea of sampling and kind of the laying out the general framework and some of the key terms that we're going to use throughout the course. So just to recall, our main focus in Chapter 6 was when we had a normal sample. So here, x1 through to xn are independent and identically distributed normal random variables with mean, mu, and variance sigma squared. So mu and sigma squared were our unknown parameters. And so there are two key statistics here that we learned about and that are we're going to see a lot both in Chapter 6 and in Chapter 7. The first one is the sample mean, which we've seen a number of times throughout the first 4 lectures. And then the second one is the sample variance, which is 1 over n minus 1 at the times xi minus the sample mean squared. And these are statistics because they depend only on the data. We're going to define this a little more formally later today. And where the n minus 1 comes from, like if you've seen sample variances, they usually have an n minus 1, sometimes they have an n. We're going to learn a little bit more about where that arises today as well, like and why we have this n minus 1 there. So the normal, like what's nice about the normal sample is that you can actually exactly determine the distribution of x bar and s squared, and that's regardless of the n. So normally what we're going to find in the course is that the distribution of x bar or s squared or any other statistics, you may not know the exact distribution, but you can use asymptotic distributions like from the central limit theorem or something. But for the normal distribution, we can actually determine and characterize these distributions exactly. So in particular, what we already know and what we've seen several times in the first 4 lectures is that x bar is normally distributed with mean mu and variance sigma squared on n. So we can use that and draw any inferences or say anything we like about about x bar from that. The next question is, what about the distribution of s squared? And this is going to relate to the chi-squared distribution that we saw earlier. So to get to that distribution, we're going to build up it with a few useful and interesting facts that kind of build up to how we finally get the distribution. Okay, so the first useful fact, and this fact is only true, so I should put in brackets So this is only true because the samples are normally distributed. So this result is definitely not true in general. But for this setting where the xi's are normally distributed, we can prove or show that x bar and s squared are actually independent. So the sample mean and the sample variance are independent random variables. And this is going to be a key building block for, we're going to see what the distributions of s squared, and then we're going to define a new statistic related to the t statistic, and we can characterize that distribution. And they all, to kind of characterize those distributions exactly, we need to rely on this fact. And it's also quite an interesting fact and quite unique about the normal distribution. So the proof idea is that, so we have that, s squared here is 1 over n minus 1 times the the sum of xi minus x bar squared. So another way to think about that is that s squared can be expressed as a function of x1 minus x bar, x2 minus x bar, up to xn minus x bar. Okay, so, if you know xi minus x bar for all n, then you can use that to say that you can use that to construct the statistic s squared. Okay, and the next key result is that xi minus x bar, let me rewrite that. So xi minus x bar and x bar are independent. So the way to think about that is the sample mean and the deviation away from the sample mean given by these xi minus x bars, they effectively don't have anything to do with each other. And the key thing here is what you can say, in fact, is that sorry, let me write this out properly. It's straightforward to show that xi minus x bar is also normal. And the reason we can show that is because it's just, you can clearly just express this as a linear combination of x1 through to xn. So we know that linear combinations of independent normals are normal, and xi minus x bar, for each xi, for each I, you can express that as just a linear combination of x1 through to xn. So you can clearly see that xi minus x bar is going to equal to we'll use this notation xj, which is just going to be you can clearly see that this is just a linear combination of independent normals. Okay, so we know that xi minus x bar is normal, and we also know that x bar is normal. So this should be a sigma squared over n. So okay, so this is a quantity that we're going to see a fair bit today and throughout the next few weeks, which is this notion of covariance. This is another important concept from 309, which is the covariance, which is a measure of dependence. So recall that in general, if you have two random variables that are independent, then their covariance is 0. The converse is not necessarily true. So if you have a covariance of 0, that doesn't necessarily that doesn't necessarily imply independence, but we know that if we'll say, well, let's use maybe the notation y1 and y2 are normal, and covariance of y1, y2 equals 0, then y1 and y2 are independent. So this is a very special property of the normal distribution. It's only true for the normal, that you have this converse result, that the covariance equals 0 implies independence. So this is not only true for the normal and not true for anything else. For any other distributions, you'd have that independence implies covariance is 0, but here we're actually using the opposite, the converse result, that the covariance of equals 0 implies independence. So all we need to show is the covariance of xi minus x bar and x bar is 0. So let's do that calculation. So I'm going to use a lot of properties of covariance here, and so if these are not familiar to you, I encourage you to kind of go back and look at some of the earlier chapters which cover covariance, or go back to your 309 notes. So the covariance here, you can, because of the fact that the covariance is a bilinear operator, you can re-express covariance as xi. You can do the subtraction outside the covariance, and so this is the property because covariance is bilinear. Another way to think about it is that covariance is basically just like an inner product type of operation. So anything that you can do with inner products, you can also do with covariances. So what do we know about the covariance of something with itself? That just equals to the variance. That's just that is just the variance of x bar. This is another property of covariance that is hopefully somewhere kind of in the back of your mind somewhere, if it doesn't sort of come straight to you. But we know that the variance of x bar is sigma squared over n, because we know that x bar is normally distributed with mean mu and variance sigma squared over n. And so now for the covariance of xi x bar, we can again use properties of the covariance. So we're just here in this step just re-expressing x bar as the sample mean. And once again, because covariance is like an inner product and a bilinear operator, you can actually just bring out this sum. Okay. And then we know that the covariance of xi xj is equal to 0. So this is just is equal to 0 for I not equal to j. So let me just write that out. Since all of these random variables are independent, we have that covariance of xi xj equals 0 for I not equal to j, and for covariance of xi is, as we know, the variance of xi, which equals sigma squared over n. Or sorry, that just equals to sigma squared. Okay. So therefore, we can say that that's just going to be 1 over n times the variance of xi, which is just sigma squared over n. And so therefore we can clearly see that So we get sigma squared over n minus sigma squared over n, which is 0. So therefore, and because, as we talked about earlier, that we're talking about the covariance of normal random variables, this implies that xi minus x bar and x bar are independent for all I. Okay. So since s squared is a function of x1 minus x bar, x2 minus x bar, xn minus x bar, and then all of these are independent. Since they're all independent of xi minus, since each of these xi minus x bars are independent of x bar, therefore we can say that s squared and x bar are independent for all n. So that's the first kind of key result. And again, everything that I say for the first, about probably 30 minutes of this lecture only applies to normal random variables. So that's the first kind of key result. So the second key result here is that, and this is going to use the first key result about independence, is that we can actually characterize the distribution of the sample variance s squared, which is chi squared n minus 1 when you appropriately normalize by n minus 1 and then divide by sigma squared. And so how can we show this? So remember that the chi squared was the distribution of sums of n minus 1. Here we've got n minus 1 degrees of freedom. So it's the sum of n minus 1 independent zi squareds. Okay, so we know that s squared equals okay, and therefore we know that if we divide by sigma squared, we can re-express this as okay, and we can further write this as okay. So all I've done here is just added and subtracted a mu, which we can certainly do. And now we just expand out the quadratic here. Okay, so all I've done here is just expanded out the quadratic on the inside here, and you can show that that this cross term is just 0. So that's some so you can show that this is 0 quite easily because you can take out the the x bar minus mu here. And then you just get okay, and so this is clearly just going to be equal to 0, because this is just going to be nx bar minus n mu. Okay, so then we clearly have that now we're getting something that starts to look like sorry, this is not actually correct, I believe. This is not actually 0. I'm sorry about that. Sorry for that error. Let me work it out properly. And that's just going to equal to n times x bar minus mu squared. Okay, and so when you put that together, what you in fact get is that this is and then that's going to be minus n times x bar minus mu squared, because you're going to get n x bar minus mu squared here, and then you're going to subtract 2 times n x bar minus mu. So that's how you end up with this expression. Sorry for that error. I guess you know that it's really like a live classroom when you see the lecturer make mistakes like that. So yeah, so sorry for that error, but you can go through and do the calculation and see that that's what that's the expression that you'll get. Okay, and so we have we can write this out as s squared. We have that. Okay, so what we know though from this is that this distribution is chi squared n, because it's just remember that xi minus mu over sigma is normal 0, 1. And we also know that this distribution here is a chi squared 1 distribution. So we have that because we know that x bar minus mu over sigma over square root of n is normal 0, 1. Okay, so we have a distribution on, so what we're going to do next is a little bit tricky, but what we can see is that we have, and then we're going to add this over to the other side. Okay, so we know that this is chi squared n. And then we know this is chi squared 1, right? So the next thing that we need, and that's kind of a really crucial piece to this, is that, so we have that s squared and x bar are independent, right? So we know that n minus 1, therefore n minus 1 s squared and n times x bar minus mu squared over sigma squared are also independent. Okay, and so what that gives us then is that so what that allows us to say is that we know that we have y. Let's just use this notation: y plus y1 plus y2 has a chi-squared n distribution, where y1 is like our this is our y1 and this is our y2. The n minus 1 s squared over sigma squared, and y2 is our x bar minus mu over squared over sigma squared. We know that y2 has a normal, it has a chi-squared 1 distribution. And then we also know that y1 and y2 are independent. Therefore, you can conclude that the only distribution y1 could be, therefore y1 has to be a chi-squared n minus 1 distribution. So this is where independence really is important, because if that s squared and x bar are not independent, you can't make the conclusion that just because you're adding a chi-squared 1 and getting a chi-squared n, that what you're adding has to be a chi-squared n minus 1. It's only true because they're independent. So therefore, you can say that n minus 1 s squared over sigma squared is chi-squared n minus 1. So we can tell you exactly what the distribution of the chi-squared is. And then finally, this is what's often called the t-statistic. I'm going to put statistic in quotes here because we have a mu here. So we actually have a mu, which is a population parameter. So this is only a statistic if mu equals 0. And in testing, which we'll see in chapter 8, we're often testing whether mu equals 0, which is why the t-test and the t-statistics is going to be a very important statistics we see in the course. But here we're just subtracting a mu to kind of, because that allows us to characterize the distribution completely. What we can then say is that this is actually follows a t-distribution, okay? And why is that the case? Because we know that square root of n x bar minus mu over sigma has a normal distribution. And we know that n minus 1 s squared over sigma squared has a chi-squared n minus 1 distribution, and that these two are independent. Remember that for a t-distribution, you need the top and the bottom to be independent. So therefore, you can see that t, you can re-express this as okay, and then this is going to then be like square root of s squared this is going to be s squared n minus 1 over sigma squared, and then divided by square root of n minus 1, okay? And so we know that this is chi-squared n minus 1, so this is going to be distributed as a z over square root of chi-squared n minus 1 over n minus 1, which is distributed exactly as a t of n minus 1 in this case. So to summarize, I mean, we have 3 key results here. Which, and sorry, one thing I should mention is that the reason why this t-statistic is used often instead of, say, the z-statistic is because you can see here that you don't need any knowledge of sigma here. So remember for z, there was a sigma in the denominator, which you may not know. Here, you don't need to know that sigma because you have the s in there. So this is, in some ways, if mu equals 0, this does not require knowledge of sigma. And so this is going to be very useful for us as well later on. So okay, so these are three key results that we have when we know that our random variables are independent and identically distributed normal random variables. So this is kind of the these take-home messages that we're gonna use later, and recall again that all of these results, none of these results are true for any other random variables. They're only true because we have made the normal assumption, the assumption of normality. Okay, so I think if you want to take a break, this is a good time to take a break before we move on to the next topic, because we're moving to chapter 7 now. So this is if you want, this is a good time to take a break. Okay, so we're coming back now to chapter 7, and so we're going to move on to chapter 7 material. So here we're going to cover a so I'm going to begin this part of the course by actually introducing a general framework. So far, for the first 3 or 4 lectures, we mainly did kind of a review of 309 material, and then we saw some new distributions and some properties when things are nice and we have independent normal samples. What we're going to do right now, because we want to make what we say a little bit more general, I'm going to define a very general framework of how to think about what we're trying to do, and this is going to be something that's going to hopefully serve us well for the rest of the course. And then we're going to move on to topics that are covered. So some of this is covered in chapter 7, and then we're going to look at specific sampling schemes and statistics, particularly x bar and s squared, related to that when we move away from the normality assumption. Okay, so this is something that I think now is probably a time you really need to sort of focus, just as I think this gives us, I'm going to go through this framework because it's going to give us a good big picture idea of what to do. And I think it's going to serve you well as just a general way to kind of pin down and focus on the specific topics you're looking at, because hopefully they all fit somewhere into this framework. So we're going to develop or discuss a general statistical framework that hopefully we can view most examples and most topics that we covered in the course through this framework. So what's kind of a statistical framework? So our goal is to do, so our goal here is to draw inferences from data, okay? And we want to do that in a rigorous way. So I should add so we want to do this in a mathematically rigorous way. So I'd say that there's 5 key there are 5 key components of our framework, and I'm going to write the framework down, and then we're going to see a couple of examples that we've already going to look at a couple of examples that we've already seen through this framework, and then we're going to be more general later on. So the first key component, as you can imagine, is the data. So we can call this the sample data. And this is typically going to be something like x1 through to xn. The second component is really important. It's the distributional assumptions that we made. So for example, up until now, we've only been talking about scenarios where things are normally distributed. And that allows us to be mathematically rigorous because we can say what the distribution, like the distribution we assume behind this data is. So is it independent? Is it normally distributed or Bernoulli distributed, or whatever other distribution we might think of? And then the other thing is there's this notion of population parameters, and that's really important here. So because typically, as I mentioned in 309, you typically know all of your population parameters a priori. So you might know that the probability of voting Democrat is 0.5 or 0.55 or whatever, but in 310, these are going to be typically unknown, and our goal is to actually use the data to try to estimate those. The third component is a statistic, or you can think of it also as an estimator. And all that is just a function of the data. So we'll just write it out as some function of the data. So we've already seen examples like the sample mean and the sample variance. These are all statistics. And the idea generally is that we want to use the statistic to try to say something about the population parameters. So the fourth component is the distribution of the statistic. And then either it could be an exact distribution like we just saw, or it might be an approximate distribution that we infer through like the central limit theorem or some other asymptotic result. And then the final thing, and what we're going to talk a lot about in this course, is so we're going to talk a lot about 3, 4, and 5, I would say. But what we're going to kind of finish with is that we want to tie back to our original statistical goal, which is to infer something about the population parameters from the estimator. So it's the inference parameters, the population parameters. From the statistic. So whenever you're thinking about a question, try to have this framework in mind of setting things up, because I would say sort of most, if not all, problems that you work on in this course, you can tie back to this framework. And I think that just kind of potentially could give you a good grounding in how best to address it, to at least think about it in the right way to begin with. So let's see like how we've used that framework in the example. So here we've seen that normal sample, this is the example we had in the previous lecture and what we started with today. So this is independent normal sample. So if we look at the first component of the framework, we just start with our data x1 through to xn. And then we have that xi, the distributional assumptions, which is normal, mu, sigma squared, and they're independent. And then we have the population parameters. Which were mu and sigma squared. So typically those are not known. Then we have our statistics, and we've actually seen 3 here. So we've seen that x bar, which is clearly a function of the data, s squared, which is also a function of the data. And then we've seen this statistic t, which is, this is just, these are all just different functions of the data. And I haven't subtracted off the mu here because if I do subtract off the mu, it's not a statistic anymore because it has a population parameter in it and is no longer dependent on just the data. Now the distribution of the statistics. So we know that distributions of and so we've learned, we've seen on a number of occasions that the sample mean has mean mu and variance sigma squared over n. And then what we learned today is that, and this is a really rare and nice example where we can characterize all the distributions exactly. And then we have that t is going to have a t distribution with degrees of freedom m-1 only if mu equals 0. So if mu is not 0, we don't actually know the distribution of t. But if mu equals 0, then we do know the distribution of t. And so that tells us and then for part 5, we could use distributions to find estimates of mu sigma squared and confidence intervals. Confidence intervals or sample error, standard errors is the right term. Okay, so this is one example that we've seen, and the point of illustrating this was just to put what we've discussed into a single framework. And now let's do a second example, which relates to going right back to the first lecture, voting in Wisconsin. So once again, our sample data is just x1 up to xn. So that's our sample data. Okay, and typically, I'd say for almost everything we see in the course, that's going to be the first component. That'll be kind of the most sort of black and white thing is the data will just typically be like a sample of size n. And then where it involves you to think a little bit is to pin down the next, 3 or 4 components of the of this framework. So we have that, recall that we made the assumption that xi is Bernoulli P, and the parameter here, or population parameters, is P. So like that's the proportion of people who vote Democrat. So I should say that this was also assumed to be independent. the statistic or estimator that we have was x bar again. So that's just counting. These are Bernoulli random variables. So counting the proportion just corresponds exactly to the sample mean. And then the distribution. Of x bar. And in this case, we can only get an approximate distribution, or calculating the exact one is substantially more complicated. So we use the CLT. So I'm going to use this approximately normal 0, 1 by the CLT. And then 5, so once again, you can you can estimate P from X bar or find confidence intervals for P. In chapter 8, we'll see how you can actually do tests of P. Like, you might be interested in just testing the hypothesis that P is bigger than 0.5. And we're going to learn how to do that in a rigorous way in chapter 8. But this is sort of how you could set up the framework in these two cases. Okay, so once again, I remind you that, if you're ever like kind of lost, just kind of try to go back to this framework just as a way of, pinning down the key things that we need to keep in mind when we're trying to understand the problem at hand. Okay, so now we're going to move on to okay, so we're going to talk a little bit about survey sampling and sample mean and sample variance related to that scenario. So the setup is you have a population. Typically, like we could say, we'll begin with a finite population of size n. So this big N is different from the little n that we've already seen. So I'm going to use this notation. So what this is that we assume that we have a population finite of size n, and then the values that this can take is, C1, C2 up to Cn. Okay, so, you can imagine that this could be people voting Democrat, and so like a 1 could be, person 1, a 0 could be person 2, and so on. Or you could imagine it being heights or weights of a certain population. So typically n is large, so or big N is large. N is large here. And then what we do is we draw a finite sample of size n. And typically, so we know that we're always going to assume that n is less than or equal to n, and often it's going to be much, much smaller than n. So we have big N for the size of the population and little n for the size of the sample. So once again, our sample data isn't really going to change. We're going to have x1 up to xn. Let's think about the distribution of xi. So what that is that it's just like you randomly pick any one of the the probability of any sample being any particular value is just 1 over n. And we're going to consider two sampling schemes. The two sampling schemes that we're going to consider are independent random sampling, which is just that draws with replacement. So I'm going to use the acronym here, IRS. This is draws with replacement. So, and it's called independent random sampling because this implies that because the draws are with replacement, what that means is x1, x2 up to xn are independent. Okay. The second scheme, which often actually happens more in practice, we're actually going to do more math around the first scheme, but I wanted to also touch a little bit on the second scheme, which is what's called simple random sampling, or SRS is the acronym we're going to use. These are draws without replacement. So what we have here is that these xi's are no longer independent. So they're not independent. But xi's are have same distribution. So so we know that so for all j, the probability of xi that you draw a particular value within that is just 1 over big N. And we could have some of these c's being the same, for example, as the voting example, to give you one concrete example, but they're kind of uniformly distributed across the entire population. Okay, and so now let's talk about, so we know now that there's effectively, we've covered the first two components of the, or we haven't, to finish the second component of the framework, we need to define population parameters. And so first one is the mean, which is okay. So this is a maybe I'll use the notation J here to just kind of avoid confusion. So this is different from the sample mean, right? This is the population mean. It's just the average of, like, if you imagine taking, and you can think of this as just the expectation of the xi here. If you imagine taking the expectation of xi, because the probability is just 1 over n for all of them, then we're just doing the probability times times the actual value itself. And then sigma squared, which is going to be the variance of xi which equals to 1 over n summation. Okay, so there's a big N here and not an n minus 1 because this is a population. So all we're doing here is using the formulas from 309 that we've seen earlier for expectation and variance applied to this random variable here. So this is our random variable, and this is the distribution of the random variable. It's just a uniform distribution over the n points in the population. And then we're going to determine what we get. Then we're calculating the population parameters, which is the population mean mu and the population variance sigma squared. Okay, so we have just to recap. So going back to the framework, we have our sample data, x1, x2 up to xn, and this is typically always going to be the case. Our distribution, which is just that xi could be any value in this sample, so the range of or in this population, sorry, and then we have the probability. So this is the distribution. It's just the uniform distribution. And then we have the population parameters for ease of just eliminating a word. I'm just going to use parameters here. That's just mu, which is e of xi. And the population variance here, which is okay, so we're up to the first two components of the framework. And the other key thing is that there's two different sampling schemes we assume. So there's going to be either IRS or SRS. So these are the, you could think of these as the sampling scheme, or independence assumptions. Okay, and the final thing I'll say today, before ending today's lecture, is third component is the statistics. And there, what we've kind of typically seen, we're going to look at X bar. So this is the sample mean. So this is the sample mean as opposed to the population mean. And then the sample variance. And this is the one where we do have the n-1, and we're going to see actually in the next lecture why that n-1 comes in. And so the question that we're going to finish with, that we're going to address in the next lecture, so what the question that we're going to address in the next lecture is, what can we say about X bar and S squared? In particular, what can we say about properties of its distribution, like its expectation, its variance, maybe something about what the actual distribution of these random variables is under the simple random sampling and independent random sampling schemes. Okay, so that's everything that we're going to cover today. and hope you enjoy the rest of your day. Thanks very much.